Okay, so then the next topic in statistical methods now actually is the general linear model for fMRI, which is a very important topic. And I hope by now you've all seen blobs on the brain in some of your papers, so reddish kind of blobs, and these are usually the outcomes of general linear model analyses. So you should roughly know what we mean by this. And you of course also have heard an introduction to fMRI, so you have a rough idea of what fMRI is. Who of you has studied the GLM previously in statistics? Yes or no? So who has studied the GLM in statistics? Did the term come up, and was it described in terms of matrices, and was there a multivariate normal distribution in the statistics at FU?
Yeah, and it was very, very big.
So how many sessions did you have on that?
One.
Okay. And how was that introduced? So what do you remember about this?
In the context of ANOVAs.
In the context of ANOVAs?
Yeah.
Okay. Okay, yeah, so a general linear model, in general, if you look at the undergraduate statistics syllabus and also the books, it usually, you find this in the last kind of chapters or in the later chapters. Although it would make more sense to actually put that into the first chapter. Sorry. Now that's one aspect of the second part of the course. The other aspect of the second part of the course is to apply it actually to fMRI. And in the past, I did courses on the general linear model with the aim of applying it to fMRI, but then the course on the general linear model basically took up the whole semester, and then the semester was over and there was no fMRI. So what I'm trying to do this year, or with this course, so these next 8 sessions, is actually to combine this, which however, so of course I also taught GLM for fMRI previously, but that means that we will not do the whole GLM theory from basic principles, which is, it might, so for first level fMRI, and it's not that important, but in the end you need actually both. So you need a full understanding of the GLM. So I will try to, try to present the GLM theory in a nutshell, specifically next time. So today we're going to just essentially do some introduction and overview, and then next time I try to condense the 32-hour GLM course into a 2-hour GLM thing. But I really recommend that you watch the lectures, and of course also the script stuff on the GLM is not quite there on my website yet because I'm currently polishing it up, but that you also look into that. The probability stuff on this, so multivariate normal distribution, that's already there, so you can also look at that. However, so one only needs this to in a way, to a certain degree, to appreciate basic stuff of fMRI in the first instance. So then, after the Christmas break, we will talk about how first-level design matrices are generated, specifically by convolution of onset functions, which you might have read about. And then we talk more about the regressors themselves. So we will talk a little bit about design efficiency, and one specific, a little bit different design, namely the FIR, finite impulse response design, which specifically if people use GLM in preparation for classifier analysis, recently plays a bigger role again. Then we talk about ANCOVA design / psychophysiological interactions, which are often portrayed as a measure to, as a means to study connectivity. They are ANCOVA designs, and we will discuss what that means. So that's ANCOVA and PPI. Then this would all be first level analysis, so the analysis of fMRI data of a given run from a given participant or multiple runs of a given participant. Then I want to do a little bit on group level analysis, so second level analysis. And then finally the last 2 sessions spent a little bit on what is also quite popular in fMRI in terms of theory, namely multiple testing problem, and then the random field theory based p-values, which we last year also spent a whole semester on, but this time I want to condense that a little bit. Because these are the p-values that you always see in papers. So that's essentially the outline for the remaining winter term statistical methods course. Yeah. Currently, I think in terms of the script, you find this GLM formulation and you find this mass univariate viewpoint stuff, which covers at least the introduction and a little bit of the GLM theory. The other ones, they are there, but I have to polish them a little bit to really be happy to share them by the website. Questions about the outline? No. So this is trying to kind of give a fairly applied perspective on the GLM rather than the GLM lectures that you find online, which are also applied, but they are more general in the sense that the GLM is of course a method to do any kind of parametric statistics in the sense of the general linear model. And here I'm trying to make the whole thing more specific to fMRI data analysis. Good, then if there are no questions with regards to the outline or anything, then let's start with some introduction. And I think the way I want to do this is in terms of my general data analytical mindset model. So you don't know how you want to call it. Today I call it data science. So what is data science and what are the aspects of it? What is data analysis? And what does that mean for fMRI? And what is everything? What is science? You can also just call this whole thing science. And this is what I'm going to do now. So what is science? So the first thing that you need to become aware of is that there are 2 things. Namely, there is science. There's science, and then there's reality. So this is a worldview. So of course you can do philosophy and debate whether there actually is something called reality or not, but the scientific mindset assumes that there is something that we want to call reality, and we want to, with science, somehow study reality. Now, science then, in this kind of data science viewpoint, starts, or not necessarily, it doesn't start with, but one essential component is data. And to make this now concrete, we are of course talking about fMRI, and we have discussed previously how fMRI data is acquired, and what we then have in the end. So does anyone remember after pre-processing how the fMRI data is organized? So if somebody has acquired fMRI data and says, here, I'm going to give you my fMRI data set, what do you get? So we had an introduction to fMRI, right? And we also talked in the at various time points about this. Maybe not clear enough. So remember that there's something called Voxel. So what is a Voxel? Yeah. And then you, when you acquire fMRI data, do you acquire one data point, or what do you usually acquire? Many voxels? And only at a single point in time or at multiple points in time? Yeah, but if you're talking about fMRI, so task-based fMRI, then a time series, exactly, yeah. So if we are doing fMRI, we talk about fMRI resting state or task-based fMRI, but we're talking about we acquire a time series of images which are organized, each image in terms of voxels. So for each voxel, we acquire a time series. Yeah? So our data and the entire data set comprises, of course, many voxels. If we, and this is already quite important, if we apply the GLM to fMRI data, what we do in first instance is that we apply the GLM to an individual voxel's time series. Yeah? So remember that there is something called voxels, and here we now have the data from voxel V, and V can be 1 to, I don't know, 40,000. There are many voxels, something like this. And for each of these voxels, we acquire time series. Yeah? So we have a data point, namely the MR signal for each TR. That's how things are usually set, although the TR is, of course, the interval between two image acquisitions. But we have data points that belong to a given voxel and that extend over time. Yeah? So these are numbers. So essentially what you have is a time series of numbers. Think again also when we talked about our YK just like a week ago, our series. This was, there we used ERP, so electrode potentials on in EEG. Now we're talking about fMRI. We talk about the data from a single voxel. Yeah? Maybe I should, rather than this, write single voxel there. And this is the data that we acquired from a single location in the brain over time. Yeah? Is that clear? That's really important that you know what the data is. Is there questions about the data right now? No. Good. So the data, that's now our time series of a single voxel of the MR signal. The data is already part of science. And this is important. So out there in the world, there might be kind of the brain of a participant. By using the whole MR scanner, we kind of record some aspect of reality, namely this MR signal for a given voxel over time, and this is our data. Why is data part of science and not part of reality? Well, because it depends, the data depends on how you acquire it, right? So if you use an EEG system or NIL system, or just kind of a phrenology thing, you always get different kind of data. Yeah? So that's the analogy is, of course, from cognitive neuroscience perspective, data is kind of the activation pattern in your retina or in your retina is, I think, the best thing because that's actually part of the brain. But of course, the activation pattern is already part of the brain or the system that then tries to make sense of that. Yeah, it's not the activation pattern in the retina is not what's actually happening outside in the world. Yeah, so data is part of science, which is already quite hard for some people to deal with. So that's the first thing. That's the data that we are also dealing with. So for the GLM, we are dealing with making some boxes here. Maybe there we have a brain, and there we have a brain area. We have a time series of the MR signal, and this is the data that we are dealing with in terms of the GLM. Now, science then has three principal components, by which I don't mean principal components in a PCA sense, but basic constituents, namely three steps in the scientific progress or the scientific process, that's what I mean, namely what I call model formulation, which you can also call theory development. So a lot of things that happen in cognitive neuroscience today, and also everywhere essentially in the empirical science, is a little bit, you have kind of empirical people that somehow do experiments, and then you have theoreticians who do theory. And this is horrible. It doesn't make any sense, but that's how it is. In general, formulating models and developing theories is the task of every scientist. Yeah? The task of every scientist is not to run the scanner all the time, chuck the data into SPM, get something out, write a paper, and then the next paper do something else. The task of every scientist is also to formulate theories and models. And of course, everybody does that. Also, the people that scan a lot do that, but you can do it to varying degrees, and you can formalize quantitative models or just hand-wavy models, or you can formulate models in terms of RSA dissimilarity matrices. You also can call this model. That's all fine, but that's model formulation. And that's an important aspect of science, and the GLM the model that we formulate for our data in this specific case is, of course, the GLM, which just for now I will write a little bit familiar for you, I hope at least, in terms of what is called multiple linear regression. And we will talk about this equation a little bit more. Let's stop here at P. So we have to talk about this more. I is here the index of the time point. Yeah, I is going from 1 to n, where n is the number of TRs, the number of volumes that have been acquired. Yeah, so that's n. So this is here is 1, 2, and so on, and then n. And the model that is formulated for this data in terms of the GLM is a multiple linear regression model for each data point. And this we will have to explore a little bit more. So don't worry if you're not completely happy with this equation right now. but we leave it at this because we will go in more detail about it anyway. But this is the model that we formulate for the time series of each voxel, and one can write this in GLM form. There are different ways to write it. In GLM form, one can, for example, write it in this way, although these days I try to not do that too much, but that's the model that we formulate. Yeah, so that's model formulation. That's the model that we formulate. I know this is different from undergrad statistics, where statistics was more like we compute this, then we compute this, and then we have a t-value, and if the p-value is small enough, we're happy. But this is not a sustainable viewpoint of anything, and it's also not interesting, and it's also confusing. So one can view all of these approaches that you learn for statistics, so simple linear regression, t-test, ANOVA, ANCOVA, and so on. One can all express them as models, then one knows what one is dealing with. There is no model-free reinforcement learning, and there is no model-free data analysis in general. So if I guess you know things like data-driven approaches and model-free business. For every of those things, I can tell you what the model is, and it makes a lot more sense to describe the things always based on the model, the mathematical model, because then you see that certain things that are model-free or that are just statistics, inferential statistics, they are actually models, and these models are maybe not that interesting. Good, but that's the first thing in terms of the scientific thing, and now of course somehow the model is not there. I mean, you have certain disciplines that just do model formulation and model analysis, so looking at the models, for example, computational neuroscience. They just like to formulate models and then play with them, simulate them, and then go home again. In data science or in cognitive neuroscience or in computational neuroscience, what we try to do is actually, when we formulate models, not only do this as a kind of a cognitive exercise, but also to somehow relate this to data. And this is then the next important step, which I tend to call model estimation. You can also, you know this also under the names of parameter estimation, parameter fitting, model fitting. All these things are the same thing. So what happens there is that based on some methods, for example, frequentist statistics, principles like maximum likelihood, or Bayesian statistics based on essentially conditional probability calculus, you tune certain aspects of the model to the data. So you try to let the data influence your model and try to predict the data based on your model. So you basically evaluate your model. Now, you don't evaluate yet, you just tune it a little bit with respect to the data, because the evaluation step will be the last thing. So in terms of the GLM, what this means is, has anyone heard the term ordinary least squares estimation? Yeah? So ordinary least squares estimation is one way to tune the parameters of a general linear model, or of simple linear regression, which is a special case of a general linear model, and which is for the beta parameter, and I think also for the variance parameter, same thing as maximum likelihood estimation. In any case, these kind of things, they fall into the model estimation business. And for example, these beta parameters that you see there, there's a formula that does this. You can also do model fitting and parameter estimation numerically, which is maybe even more popular in kind of the model-based cognitive neuroscience, where model fitting is usually done numerically by basically shifting around the parameters of a model and then trying to match the quantitative prediction of the model best to the data. In terms of the GLM, the way this is done is usually using ordinary least squares, or more specifically, general least squares and restricted maximum likelihood estimation. We will deal with that, not very much, I have to say, in this course, because I'm focusing more on the model formulation and the different intuitions that come with it, rather than that, because we would have to go more in basic steps about what is likelihood, what is the likelihood, what's the maximum likelihood estimation, and so on. It's all very interesting. If you want to learn more about this, there are the videos. Otherwise, you're welcome to do a master thesis only on this. So now we've fitted some parameters of our model, and then the last step is actually model evaluation. So of course we have to then somehow make a statement of is our model now good? Is it a good model of the data? That's essentially the question. And these kind of questions, so there are two things. So one is to look at a little bit more at the fitted parameters and do kind of model conditional inferences. These are the t and p values that you see plotted on the brain. So there you see some t values, so it's some red blobs, yellowish red blobs, which reflect the ratio of the beta parameter estimates and the variance parameter estimates. So this is kind of evaluating the estimates that come out of a model and then saying, okay, this means that and that. The other question that is more general is whether the model itself is a good model. So this is something that you can do with f-tests, or you can do with marginal likelihoods or model evidences. You can also do more things. You can also do things if you're doing the whole Bayesian machinery. You can do things like model averaging, which is an estimation scheme and so on. So if you know about these things, I promise you we will fit them into this framework. In general, the last step and the step that we are actually after here in the end for the GLM is to look at t and p values, so do some model conditional inferences. And then, of course, the scientific approach would be to, once you have done that, so you've developed a theory, you somehow adapted this theory to your data, because you allowed for some free parameters in your model, some degrees of freedom, you evaluated that, and then of course you don't find that the model is best and you're done and science is over, but that you can improve something, and then of course you would go back here to now formulate a new model. Yeah, so what I'm trying to tell you here is that on the one hand there are these very general components of science and dealing with the data in general, namely so these steps: model formulation, model estimation, model evaluation. And on the other hand, they can be specific, for which I now use red and make the whole thing more messy. Specifically for the GLM, for fMRI, they take the form of multiple linear regression, or the GLM. They take the form of ordinary least square or maximum likelihood estimation for beta parameters, also for the variance parameter, and they take the form for of t or p values or f values for classical inference in terms of fMRI. The data that the whole thing is applied is always the time series of the MR signal of your voxel. The GLM, and this is the mass univariate, which is of course fMRI specific. The mass univariate approach is to consider one GLM for each voxel. So essentially you have this map of voxel values, voxel time series, and you analyze each one individually. If you think about what's actually happening, and you are at one point also familiar with the random field theory approach to the p-value evaluation, at one point, at least I, realized that if you use the p-values that are in the SPM table, you're actually not using a mass univariate viewpoint, but you have a spatial temporal model all the time, which is a random field model. However, this is evaluated for computational efficiency in a mass univariate manner, and the general lingo about the general how people think about fMRI GLM analysis is mass univariate. So although I think that if you derive your p-values based on the SPM table, you're not doing a mass univariate analysis when you are using GLM for fMRI. De facto, everybody else, including myself for the longest period of my life, thinks and thought that this is a mass univariate approach. So it's fair to say that this is a mass univariate approach. Yeah, sorry, but in the end, so the thing is also I don't want to change my whole script and start with the random field theory, because this is really not how. First of all, it's much harder to introduce that, because we would have to start with random fields from the very beginning. And the other thing is just the whole world thinks of GLM analysis of fMRI as mass univariate and not as a spatiotemporal random field model. Okay, questions about this general framework of science, data science, model-based cognitive neuroscience? Yeah.
Yes. So I think I got the basic idea, but it's hard to imagine. So how would a formula look like if I have the simple hypothesis about brain activation? For example, if I say one voxel should be more activated than the other one, so would Y in this case represent stronger signal or higher frequency, and then X would be associated?
Yeah, so you are of course strongly influenced by the hypothesis testing framework that they hammer into you in undergrad statistics. I have to say I never, so I've been doing a lot of hypothesis testing this year essentially, and thinking about hypothesis testing because we did this random field theory paper, and now I'm doing the part 2 power paper. So first of all, hypothesis testing is horrible, because what it corresponds to is partitioning a parameter space into two partitions, and then forgetting all the information that you have about the parameter in terms of its parametric value, and just deciding whether it's in one partition or the other. So whether it's 0 or it's different from 0. This is typical binary hypothesis testing. So that's the first thing. The model, I'm not quite sure whether so the way I would see if you come with hypothesis testing, let me think about it. I have to actually make this up now.
My question is not about the specific about hypothesis testing, but rather about what do those parameters in the formula represent actually.
Yeah, this is what we will talk about.
Okay.
But hypothesis testing, so the way I see hypothesis testing is that you have a probabilistic model, and you also, I think the crucial thing about hypothesis testing is in a way the model evaluation, because you somehow estimate the parameters and then you check whether the parameters are in one partition of parameter space, and then you somehow make your decision based on whether they're in this one partition or the other partition. It's an interesting exercise, but this goes beyond what you were actually interested in, I think.
It's just, it's hard to imagine from those abstract formulas how they represent brain activation.
Yeah. I mean, this is the whole topic of the of everything between now and mid-February. Yeah, so this is what we will try. The hypothesis testing business is okay, then something different. Other questions right now? No. Okay, then maybe we actually follow up there, namely with the model formulation for our fMRI time series, and actually essentially this question that you just asked, namely how does this relate to brain activity? But because you said hypothesis testing, I was a little bit off there. So that is, how do I call this here? Brain mapping using the GLM. So this is kind of a first intuition how the formulation of the GLM and this idea that some brain area lights up, how they actually go together. Not by going into all of the technical details, but by giving you an overview. So what we established so far with a little bit of notation is the following. We deal with a time series again, like in Fourier analysis, but we're now using actually a different model. Maybe you also realize that. So in Fourier analysis, we use this sum of cosine functions to model a time series. Now we use the GLM as the model. We can actually, and this is also what's done in GLM for fMRI, one can also adapt the GLM to be kind of a Fourier analysis model. This is actually what's happening in the design matrices in SPM, because there is this cosine basis set which you never see, but which is in there and does the filtering. There's just a side note, but here we have the data that we are interested in now, and this is how I write this. So we have, and maybe the graph next to it, we have the MR signal, and each value of this MR signal is called Y now, and it has an index which corresponds to its TR during the run, or multiple runs. So you can think, if you have, it's always one voxel, but you have multiple runs in an fMRI experiment, then you have for each run, let's say, 200 images, so 200 sequential data points for this voxel. Then you have 4 runs, then you have 4 times 200, so 800 data points. So that doesn't really matter, but the important thing is that the data is here really the MR signal, and in total there are n values, and this MR signal, we will look at some simulated data later, does this. Now it looks a little bit like an HRF, but this is not an HRF, this is just the entire data from a whole run, yeah? So, I don't know, maybe it looks like this or something. This is written as Y, so as this long list of numbers, and one can also simply say that this is an n-dimensional vector, and vectors are usually thought of as columns. So this is why here again, like in neurocognitive methods, we have the transpose sign so that we have a list of numbers. So to make this very concrete, something like this. Yeah, so this would be our data, our data from a single voxel now. Yeah, many values. Good, and what I already introduced briefly on this other slide was that the fundamental idea really of applying the GLM to this kind of data is to do a multiple linear regression. And that's the same multiple linear regression that you learned in undergrad statistics. Yeah. So multiple linear regression, I don't know how you wrote them. A good way to write them, or one way to write them, is, which is also good, is this way. So what are these things? I get rid of this, then I have a little bit more space to annotate things, and I use a different color because that's visually amazing. So yi is the ith data point, So that's, for example, if I is, I don't know, 5 here, then this thing here is y5, yeah? So that's the ith data point. So that's one number in this list of numbers, yeah? So I is an index, and it runs from where to where? Well, if you look at this one, 1 to n, yeah, actually in the Fourier analysis business, it always ran from 0 to n minus 1. Here it now runs from 1 to n. This is also why I always struggle with this 0 to n minus 1, because I'm a MATLAB person. Indices run from 1 to something. So this equation here then describes the model for one of these data points. Yeah, it's not for all data points, it's just for one data point. But the model is the same for the different, so it needs in structural form, not in its actual values, but in its structural form it's the same for all data points. From multiple linear regression in undergrad statistics, does anyone remember what these xi are? Maybe they were called different, but usually they're called x. Does anyone remember what that was? Or what do you remember about multiple linear regression?
These are the factors,
yeah,
according to which we estimate the.
Maybe just say the factors, that's one way one can call them. Anyone from simple linear regression? No, they are not the parameters. The betas are the parameters. The predictors, that's kind of a little bit more the language that is applicable specifically if these predictors take on continuous values. So factors is more the language if the predictors take on what is always called dummy variables or something. So if they only take on categorical variables like ones and zeros, they are called predictors, usually more in the context of regression. Does anyone else know a name for those things? Or wonders whether other term you have in mind is the same thing? Sorry? Coefficient of correlation. No, the coefficient of correlation, no, that's completely, sorry, that's completely, so the coefficient of correlations, they are actually, these are, coefficients of correlations are entries in the covariance matrix of the multivariate Gaussian, and no, so this is also maybe important, this is regression, not correlation. You have another?
I know it's the same in English, in German we have regressor.
Yeah, regressors, the same thing. Yeah, so the xi, they are called variously. So the most general term actually is independent variable. That's the most general version. But if you are dealing with multiple linear regression and simple linear regression, they are usually called regressors or predictors. And in terms of ANOVA designs, they are also they can also represent factors. So they are not quite factors, but they can represent something like factors. We will talk about that more when we talk about ANCOVA. However, in regression designs, they are more often called regressors, predictors, independent variable. Forget something? I don't think so. We will have another term for them? No. Good. One thing is important in terms for these regressors, predictors. So I think I mainly call them regressors, or I call them columns of the design matrix. This is actually another term, design matrix columns. But these regressors, there are two things that are important. So first of all, there are what is also often lost in undergrad statistics. They take on different values based on I. This is why they have this I index. Yeah, so the values can vary with I. Very important is that, of course, the regressors and the predictors are known. So you know them, you measure the data, but you know the regressors and predictors. This is actually an important part of model formulations. So they are known. And you should also, so in the setting that we are dealing with, they are also not, they are deterministic, so they don't represent a sample. So correlation models look very similar, and a lot of times people actually sample some. So they sample, so for example, the yi is, human size, and then x is age, maybe. And then people, what they do is they invite people to the lab, take their age and take their height. That's what I mean by size, the height. And then they come up with these regression designs where they regress height, so that would be the yi, on age, which would be the xi. But then this is not really what I mean here, and this is also not really regression. This is, from my perspective, correlation. Regression is when you decide beforehand, I want these ages, and then you invite people of age 1 to 30, and you measure their heights, so that the axis specifically in fMRI, these axes will relate to the presentation times of your experiment, and while you might sample them, they don't act as random variables, but they are fixed values. So this is important. Try to dissociate this, because I think this is usually not clearly dissociated in undergrad statistics. So they are known, the regressors are known, they can take on different values for different indices y, and there can be p of them. Yeah. Before a break, let's briefly finish this, namely with the parameters. So the betas are the parameters. You can also view them as weighting coefficients, so they weight the regressors. Anyone else a different name for them? So in fMRI they are typically called beta parameters, because it's the beta. What I really don't know, because I never found a mathematical description thus far, but I also haven't looked enough, of structural equation modeling, is whether factor loadings are the same thing as parameters. I have the suspicion that they are, but I'm not completely sure. These are the beta parameters, and how they relate to brain activity. This is what we'll see in the next hour. Note, and this is very important, parameters are they are estimated and not known before you have the data. Yeah, so they are estimated or fitted, and they are constant for different values of I. Yeah? So they don't have an index I. So you have the beta parameters are constant over data points. Yeah? And there are as many as there are regressors. And then finally we have something that is of course the most important thing, but also the most, what is unscheinbar? I don't know. This thing, this is an error term, and for the GLM that we are dealing with, we will assume all the time that this is IID, and so independent, identically distributed, and Gaussian. This is not a necessarily assumption that you have in all regression or multiple linear regression. You can do multiple linear regression happily without assuming any Gaussian error terms. But if you want to do parametric inference on the model, which you do when you want to get the p-value out of your SPM table or your FSL table or wherever, then you imply that this is Gaussian. And we will talk more about this Gaussian assumption, I guess, next time. So because this is actually very important, because it renders the whole thing a probabilistic model. But it's also not that important, on the other hand, to understand the basic intuition of how beta parameters relate to brain activity. Other questions about these nomenclatures right now? Something that you remember different?
Has the error term anything to do with the noise?
Yeah, that's the noise. So that's it models the noise. So what this means is it models the unexplained variance. Yeah. So this is a good point to bring this up. So there is a deterministic aspect of this model. So all of these x beta, they are things that. So the x's you know about. The x's are things that you think influence yi. But then yi can still be different, and to model this variability in yi that is not explained by your regressors, you assume that there's some noise. But this is not. This is always where when people talk about noise, the whole thing is always. This is where I get this from now, because I recently with Toby Donner, when he was around here, he talked about noise. This is unexplained variance. Yeah. There was Lina. You had another point?
Just to be sure, n are different time points, right?
Yeah.
Spatial, not different boxes, but different time points.
Exactly. So this is very important. So and this will also be the nomenclature that I always use. N are the number of time points. Voxel doesn't have an index because we are dealing with one voxel only. So it's always just one voxel. And P is then always the number of parameters of beta parameters. There's one more parameter that you don't see here, namely the variance parameter, but it's the number of beta parameters or the number of regressors. So you always have as many beta parameters as you have regressors. Yeah? Okay, then let's have a break, and after the break, look at some pretty pictures.